implicit differentiation. So specifically, we'll be taking a look at how to find the horizontal and vertical tangent points. So now we'll take a look at an example. So we're given a regular function as x times y squared plus y cubed equals 5. And we're told to find dy over dx as a function of x and y. First, we'll do our implicit derivative. So with implicit derivative, we're going to do dy over dx with respect to x, right? So this is what it would look like. And then we'll do the same thing for our right side of the equation. However, we know that when we do the derivative of a constant, we'll just get 0, so we can just set this equal to 0. Right, so then here we're going to use a product rule. So it doesn't matter which term you start off with first, but we'll start with x first. So the derivative of x will just be 1 times y squared plus, and because we did the derivative of x, now we're going to leave that alone and now do the derivative of the second term. So that will be 2y. And because we're doing this to respect to x, we'll have to do dy over dx. And then the derivative of this, we'll use power rule plus 3y squared, and then with respect to x, with dy over dx. And now everything that doesn't have dy over dx will have to move to one side. So let's create a bit more room. So if we move y squared, right? First off, I'm gonna reorganize this part just so it looks a bit more neater, a bit more neat, I should say. Which I'm just gonna move the number to the front. Everything's being multiplied, so it doesn't matter how I rearrange these, because at the end of the day, they're still being multiplied. So I have dy over dx plus 3 times y squared, dy over dx, and then we're gonna subtract y squared to move it to the other side, and it's gonna give negative y squared. And we can see that both these terms right here have dy over dx, so we can actually factor dy over dx. So we dy over dx times 2 times xy plus 3y squared is going to equal negative y squared. So we can divide this whole thing by whatever's on this side to separate dy over dx. And we get this like this, right? 3y squared. And whatever we do to one side, we do to the other side, plus 3y squared. Okay, so we know our derivative, right? dy over dx is going to be equal to negative y squared over 2 times xy plus 3y squared. Okay, so now that we have our derivative using implicit derivative, right now let's start off with finding the horizontal tangent first. So with the horizontal tangent, it's basically that our derivative is equal to 0. And because we have a fraction, we'll just set the numerator equal to 0, because that's when the derivative can only be 0. Because if the denominator is equal to 0, that would be undefined. And we're not trying to find when it's undefined, rather when it's equal to 0. So we're going to set negative y squared equal to 0. So we can tell right away, like, let's say we multiply these by negative, right? We get y plus positive y equals positive 0, which is not a thing, but let's just, for the sake, let's just move this. Right, we square that, we get y equals 0. So that gives us a relation that doesn't tell us everything. So we can plug this back into our original function, right? So here, let's plug in y equals 0 into our original function. So we have x times 0 squared plus 0 cubed equals 5. So if we were to carry all this out, simplify this out, we should get 0 equals 5. However, 0 cannot equal 5. This is a contradiction. So therefore, there is no horizontal tangent for this whole, for this specific function. But let's say if for an equation or a function that did give you a true value, a value where x did equal some sort of value, to find the specific points, you would just take that value that you get. For example, you get x equals 1, and you got y equals 5, or y equals 0. You just plug these back into here, and then you get your, you should get your coordinates for that specific point once you're given your x value. So in this case, right, let's say we plugged in, I don't know, let's say our y equaled 5. So we would plug that back into our original function, right? And then let's say we plug that value into here, and we got x equals 1. Then we would plug in 1 here, and let's say we got y equals 5, right? So we could have y equals 5 because that's our x value, and then we plug this back into here, and that was our y value when we plugged in 1. Obviously, that's, for this case it wouldn't work, but for other problems, that's what you would do. That's how you would approach finding the horizontal tangent points. Now, for a vertical tangent, we know that a vertical tangent is basically when your slope is like this, right? This is slope, and when it's a vertical line, it's just undefined, right? You can't define it. It's not a slope of 0 like how we are finding with our horizontal tangent. Vertical is just undefined. So it is when dy over dx is undefined, right? So when it's undefined, the denominator, right, or bottom value is equal to 0, because when the denominator is equal to 0, it's undefined, right? So we can just say our denominator, 2xy plus 3y squared equal to 0. Okay, and then we can just subtract negative 3y squared to both sides, 3y squared, and we'll get, here we're going to move this right up here. We'll have 2xy equals negative 3y squared. And then let's separate only x, so we're going to divide it by 2y over 2y. And we get x equals negative 3y squared over 2y. Okay, so once again, this gives us a relation. This does not give us our answer. So then, now that we have x equals negative 3y squared over 2y, we're going to plug that back into the original function. So we're going to plug negative 3 squared over 2y times y squared plus y cubed equals 5. Right, so once we have that, with multiplication, we can just multiply it straight across. So we have negative 3y to the power 4 over 2y plus y cubed, right? But we have to figure out a way where we can have a common denominator so we can be able to add straight across. So we do know that for this specific function, right, this one, we do have something in common. We have a y. So we can take out a y here and make this 4 into a 3, right, because we're taking a y, right? Because if you go back to your exponent rules, right, you have x a over x b will be equal to x a minus b. And that's essentially what we're applying to here. So now this would be negative 3y cubed over 2, right? So now we need to have a common denominator of 2, and we can easily do that by just putting the 2 here and then dividing this by 2, because 2 divided by 2 is just 1, so essentially we're adding nothing, or we're multiplying it to nothing, and we can just add 2y cubed over 2. Now that we have a common denominator, we're able to add across, so we just have negative y cubed over 2 equals 5, right? Because this is still equal to 5 from here, right? So we're still bringing that 5 down. So now that we have negative y cubed over 2 equals 5, right, we can solve for just y separately. So we can multiply both sides by 2, just so we can get rid of the denominator 2. So then we'll have negative y cubed equals 10, because 2 times 5 is 10, right? We can remove this, this negative. So then we can remove this negative by multiplying both sides by negative. So we'll have positive and a negative, and then we can cube root this. So we have y equals negative 3 cube root of 10. So now that we have this, we can just plug that back into our previous relation, right? Because we previously stated that x equaled negative 3y squared over 2y, which we can further simplify this, because remember the basic exponent rule we talked about, where we can just cancel these, and we can get x equals negative 3y over 2, right? We can plug in our y value just straight into here, this more simplified version, so we can get x equals negative 3 times negative cube root of 10 over 2, which negative times negative just becomes positive, so we actually have 3 cube root of 10 over 2, which is our x point. So now that we have our x and y, we can create a ordered pair, which would be 3 times cube root of 10 over 2, and then our y value would be negative cube root of 10, and that at that specific point we have a vertical tangent. And yeah, that's basically how you find your horizontal and vertical tangent. Remember, horizontal is when the numerator is equal to 0, or when your derivative is equal to 0, while your vertical tangent is when your derivative is undefined, or where your denominator is equal to 0.